Alright, hello and welcome back to Provopolis. It's a great Monday, so as always we will be doing physics content on Monday. Not too much to talk about, so we're just going to jump into the lesson and hopefully learn a lot. So let's just get into it. What are we learning about today? Well, we are talking about uniform circular motion, which is a little bit obscure. Like, why are we looking at circles all of a sudden? But it's actually really important when it comes to physics, and it's kind of a fun topic. I really like it. I think it's fun to think about. So yeah, we're going to be talking a lot about circles. And the good thing is we don't need to know too much about circles to do well in this unit. We just have to learn as we go. So yeah, this lesson should hopefully be pretty short, but nonetheless should be quite exciting. So let's get started. And as always, we will begin by going through some definitions, getting some things cleared up before we head into our practice problems. So there's not too much that we need to cover with circular motion. But first, let's see what happens when we have something that travels in a circle. If my pen is tracking an object, right? I start at some point, and then it goes in roughly a circle. We can see that as I was tracing that circle, quite a bad circle, I must say, as I was tracing that circle, my pen wasn't going in one direction. Like, if I was drawing a line, then my pen is going in one direction, we would say, for the most part. Here, when I drew a circle, it was constantly changing. So what does that tell us? Well, when we're looking at velocity of an object, we can say that when an object is traveling in a circle, the velocity is always changing because the direction is changing. So think about like how I drew that circle. I can't just keep my pen going in one direction because I'll never create a circle. So the direction is always changing, which means velocity is changing because velocity is a vector which has both size and direction. So direction is changing, velocity is changing, and what does that tell us? Well, when there's a change in velocity, there must be some acceleration present. So there must be some associated acceleration. And, well, we call that acceleration centripetal acceleration. Centripetal. Very important to get this right. I think a lot of people think that it's called centrifugal, centrifugal with like an F. That is incorrect. This is centripetal acceleration with a P, and we denote that A sub c. So when we're dealing with circles, the acceleration is centripetal acceleration. And, well, what is the direction of that acceleration? Because acceleration is a vector. The direction of that vector is towards the center of the curve. So if we go back to this circle here, and we just take some random point here, I traced through it like that, so the acceleration is pointing towards the inside of the curve. So that's the acceleration vector. And, well, we have a formula for that. So a sub c equals v squared over r. We're not going to worry too much about how that formula came to be. This is just something important to know. So a sub c equals v squared over r. And now we define centripetal acceleration. Well, we should probably define something called a centripetal force, right? We've talked a lot about forces. There should probably be a force associated with this, and there is. And that's basically just any force that causes circular motion in an object. So now it's important to note that the centripetal force isn't necessarily a brand new force, meaning it's not a force like gravity or the normal force where it's like present. Rather, we can label some of these forces we've already learned as centripetal. So we'll see examples where the normal force is the centripetal force because it's causing the circular motion, or maybe tension is the centripetal force. So we won't worry about that too much right now. We'll see more examples in just a bit. And again, the direction of that force, because force is a vector, is also towards the center of the curve. And well, if we use F equals ma, but now we'll use this subscript c to denote centripetal movement, circular movement, then we say, okay, F equals ma, which we're used to, and we know a sub c equals v squared over r, so we substitute that in, and we get F sub c equals mv squared over r. And lastly, this last bullet point here, not super important, but it can help with some problems. Sometimes we're asked about banked curves. Something is negotiating a banked curve. So basically what's happening is we have an object moving in a circle on an incline. So I like to think about NASCAR. If you're familiar with NASCAR, there's cars and they drive around a track, right? But the track isn't necessarily flat. Sometimes it's angled, so that way the cars are traveling at an angle. So that's what a banked curve is. It's motion at an incline, like NASCAR. Cool, so those are the main concepts surrounding circular motion. So now I have this great formula in big letters, F sub c equals F net inwards minus F net outwards. So what exactly does this mean? Let's think back to when we were doing normal forces, not like F sub n normal force, but like the forces we're accustomed to in simple like linear kinematics, linear motion, stuff like that. Ignore circles. When we sum the forces, like we used to do sum of the forces equals ma, and let's just look in the x direction. What we would do is we would say that the sum of the forces would be the sum of the forces in the positive direction minus the sum of the forces in the negative direction. So we could say that this quantity here is actually the sum of the forces x in the positive direction minus the sum of the forces in the x direction, but the negative x direction. And we said that was equal to max, right? And similarly for like the y direction, you can imagine like a block on a table, it has fg pointing downwards and fn pointing upwards, and we would say, okay, the sum of the forces in the y direction is may, and then we would say, okay, fn minus fg equals may, because fn was pointing in the positive direction, fg was pointing in the negative direction. This is a very similar thing here, except now we're saying that the positive direction is inwards and the negative direction is outwards, just by convention. So that's our little formula for F sub c, the net centripetal force. So now we see a nice cleaner diagram with a much better drawn circle than what I could do. So we have this dotted path, which is the circular path, and the blue dot up here is the object that's traveling. So at this instance in time, its velocity vector is pointed towards the right. This is key, very important. The velocity vector is tangential to the motion of the object in the circle. Okay, what does that mean? Tangential means that it is tangent. So when we have a line that's tangent to a circle, the line touches the circle at just one point. It doesn't pass through the circle and maybe touch it at 2 points. That's not a tangent line. And it doesn't miss the circle entirely. It only touches at 1 point. So when we see here, we're at this point, the tangent line, it should probably pass through that point, right? Because why else would we, like if we were just looking at a random tangent line, like what's the point in distinguishing this point? So there's only one line that passes through that point, which is tangent to the circle, and that is this horizontal line right here. And that is why the velocity vector is horizontal at that point. We can look at a different point. Let's just say I take this point here. Maybe I won't use red. Let's use a different color. Let's use pink, because that's a lot different. Let's take a look at that point here. Well, we can imagine the tangent line, so it'll be something like that. I shouldn't have used pink for that. I'll use red, orange for that, I suppose. So the tangent line is something like that, where it touches the circle at just one point. So then the velocity vector is something like this. I mean, it could also be in the opposite direction, right? It could still point in the opposite direction along the tangent line, but since up here the point was traveling clockwise, I just stuck with it there. But it's perfectly fine if the object was traveling anti-clockwise. Then the velocity vector would be completely opposite, in the opposite direction, but still along the tangent line. And another thing to note is that if we draw the line from the center of the circle to the point, that forms a right angle with our velocity vector. So those are just a couple of tricks to help you determine what the velocity vector is. And then we see here that, okay, this is the force vector, that's pointing inwards, which is what we discussed previously, so that's good. And the acceleration is also pointing inwards, so that's good. If we look at this point here, this would be the force vector, and then the acceleration vector would also be pointing in this direction. Cool, so that's our visualization. And just like that, that concludes the content. So we're just going to jump into problems right now, and we'll start with this pretty simple problem. So we're asked to find the magnitude of centripetal acceleration of a car following a circular path of radius 100 meters, traveling at a speed of 20 meters per second. Okay, so let's first draw it, and I'm going to use some tools here. So we have some sort of circular path. Oops, the style is a little messed up. So that's our circular path. And we have a little car on it, which I'll just make it as a circle. And it's traveling along the circular path, so we don't really know which direction, but let's just say it's traveling clockwise. So I drew my velocity vector there. Note how it's tangential to the circle, which is good. And we are tasked to find centripetal acceleration. So A sub c equals question mark. What are we given? Well, we are given the radius equals 100 meters. And we are given the velocity, or the speed rather, is 20 meters per second. And we're given speed because it's hard to specify a direction with this. So it's fine because in our calculations, when we incorporate velocity, we mostly care about the magnitude. In this case, since we can't really define a direction nicely since it's traveling in a circle, we just let it be. And, well, this should be pretty simple. We had a formula for acceleration. We said that a sub c equals v squared over r. And, well, we have v and we have r, so we can just plug it in. So this is 20 squared over 100. So that's equal to 400 over 100. And that is equal to 4. And then we need units. So acceleration... this is in meters per second squared. And you can check that by seeing that velocity is in the numerator, so its units get squared. So that would be meters squared per second squared. And then radius is in the denominator with units meters. So one of the meters cancel out, and we're left with meters per second squared. It's just a sanity check. But yeah, that is our answer. Pretty simple. So let's move on to the second question. So now we have a ball attached to a string which is whirled around in a horizontal circle having a radius r. If the radius of the circle is changed to 4r and the same centripetal force is applied by the string, the new speed of the ball is which of the following? So first we have to figure out what in the world is a horizontal circle, which is a very valid question to have. So in physics, we define horizontal circles and vertical circles. So a vertical circle is something like this, where obviously that's a circle, but x is the center, and let's just say that there's a string here, and we have like a little ball, and we're swinging it in a circle. So Let's see if I can demonstrate this. So if you were to imagine my arm going out, and I spin something like this, right? I guess it's hard to tell, but my arm is moving in a circle from front to back, like a very normal arm exercise. I am creating a vertical circle because I'm tracing the circle out vertically in comparison to the ground. So that's what a vertical circle is. Okay? Well, then what's a horizontal circle? This is a little harder to draw, so bear with me. It's something like this, right? And now you're just thinking that's just a really flat circle. But what's going on here is like, this is the ground, right? This is the ceiling. And maybe the string now, maybe is connected to the ceiling, and the ball is like that. So now, how do I demonstrate it? Now the circle is going this way, like you're stirring a bowl. Ooh, that was such a good idea. Like you're stirring a bowl. You know, you're tracing the circle parallel to the ground. So that's a horizontal circle. So vertical circle is my arm exercises, and horizontal circle is you're making some soup. That's how you remember it. You're welcome. Okay, so now we figured out what a horizontal circle is. Let me just label these so we can remember them. So now we have to actually solve the question. What's going on here? So if the radius of the circle, it's currently r. So let's just zoom in here, and we have this radius being r. Brilliant. And then it gets changed to 4r, but let's not worry about that too much yet. Let's just first figure out what do we know thus far. Well, we reference centripetal force, and that stays constant in between the two settings. So what do we remember about centripetal force? Fc equals mac, right? That's just F equals ma. We should know that by now. And we remember a sub c equals v squared over r. So this is equal to m times v squared over r. Okay. Well, we kind of have r, and we don't really have velocity, but that's what we're trying to find, the new speed of the ball. And mass we don't really have, but the mass of the ball stays the same in between the two things because we're not changing the ball at all. So let's just solve for velocity because that's kind of what we want to figure out. So from here we can see that f sub c times r equals mv squared. That's just multiplying both sides by r. This tells us that v squared equals f sub c times r over m. And that tells us that v is the square root of f sub c times r all over m. Okay, so now basically what this is telling us is that if we have the magnitude of the centripetal force, if we have the radius, and if we have the mass, we can compute the velocity of the ball. So let's just pretend like we have those quantities initially. We know that we're at a radius r, and, well, we don't really know what the centripetal force is, and we don't know what the mass is, but we can just leave it as an expression that initially the velocity of the ball is this. But then it gets changed to 4r. So let me use a different color here. So v nu. Now we want to find the speed when this becomes 4r. Well, it's still the square root of something f, something r, something m, right? Well, what stays the same? The mass stays the same because it's the same ball, and we're given that the force is the same, right? The same centripetal force is applied by the string. So the Fc stays as well. The only thing that changes is now the radius is 4r. And you're like, okay, well, we can take out the square root of 4 term and multiply that by Fc times r all over m. And you're like, okay, that term there is right there. So now we have the new term in terms of the old term, So this is just equal to 2 times F sub c times r over m. So that tells us that V new equals 2 times V old, where this is V old up here. So that means the answer is D, twice the original speed. Cool. So yeah, I think this is a very helpful question. But let's just move right along. We're speeding through this, which is good. So now, inside a washing machine, the radius of the cylinder where the clothes sit is 0.5 meters. In one of its settings, this machine spins the cylinder at 2 revolutions per second. That is very fast. What is the acceleration of an item of clothing? Okay, so as always, I'm going to create a wonderful work of art to demonstrate what's going on here. So we have like the cylinder here. That's not a very good cylinder. I should probably like extend it this way or something. I can't draw very well. That doesn't look like a cylinder at all now. I messed it up. Okay, that's our cylinder. It's bad, but it's a cylinder. And we have some clothes, which I'll just make it as a little blob up here. And we know that the radius is 0.5 meters. So that's 0.5 meters. And then it spins at 2 revolutions per second. And we're asked to find what is the acceleration of the item of clothing. So A sub c in particular, because circular motion, is question mark. Well, let's just use our formula from question 1. A sub c equals v squared over r. We know what r is, right? This is r right here. R equals 0.50 meters. But we don't have velocity. Well, we sort of do. We're given revolutions per second, 2 revolutions per second. That's not quite the units we want. We want velocity in meters per second. So let's see if we can figure this out. V equals 2.0 revolutions per 1 second. It's just a little bit of dimensional analysis. Our denominator is good, right? We want it in per second, meters per second. So we just have to sort of change the top part instead of revolutions to be meters. So here we want to cancel it with 1 revolution. And now we need to figure out how many meters are in 1 revolution. Well, first of all, what is a revolution? A revolution, besides being the thing that America did in 1776 and before, basically means that in this case, the clothes go through the circle once. So from its starting point to its ending point, 1 cycle is 1 revolution. You can also think about it as like in terms of the Earth and the Sun. The Earth makes 1 revolution around the Sun in 1 year, 365 days. So that's a revolution. So, can we convert this to meters? Yes. A revolution is basically the circumference of the circle, right? In 1 second, the clothes go through the circumference twice. So let's just compute the circumference of the circle. We use 2 pi r, so it's 2 pi, and then the radius is 0.5 meters, right? 1 revolution, simply the circumference. And now if we compute this out, we'll see that this is equal to 2 pi meters per second. So now we have velocity in the units that we want. And now we can just plug it in. A sub c equals v squared over r, which is equal to 2 pi, quantity squared, all over 0.5. And if we compute this out, we get this is 79 meters per second squared. And thankfully, that's one of our answer choices. That is choice D. So that is our answer for this question. Pretty good. Okay. So yeah, let's move on. Question 4 now. Okay. So now we have a block and a string traveling in a vertical circle. Okay. Hopefully we remember my demonstration of a vertical circle from just a couple moments ago. And the block moves at a constant speed of 10 meters per second. And now we're curious, what is the force of tension at the top of the circle and then the bottom of the circle? So let's just handle these one at a time. We'll do the top of the circle first. So, well, we're looking at forces, so whenever there's a force problem, it's always a good idea to draw our free body diagram. So let's just zoom in a little bit here, and I'm just going to draw the top part of the circle, right? So this is, what I just drew is that top part right there. And now I'll just use a dot to represent our block, just to keep it easy. So at the top, what are the forces being applied on that block? Well, it's a vertical circle now, so my arm is like moving in a circle vertically. At the top, the block should be experiencing gravity. Even for a horizontal circle, the block is still experiencing gravity, no matter what point of the circle it's on, so long as that it's moving in the air. So there's gravity pointing downwards, F sub g. In addition to that, there's a string. It's attached to a string, so that means there's tension. So also pointing downwards is F sub t, right? Because at the top, the string is vertical. So those are our two forces. Are there anything else? Normal force? No, because it's not on a surface. Friction? Nah, it's just on a string. And anything else? No. So those are our two forces. And, okay, well, let's just sum the forces. So we sum the forces, but what's the direction? You might be tempted to think that it's the y direction, right? Because they're both pointing in the y direction, not in the x direction. But the thing is that the block is traveling in a circle. So we don't really have this direction. We have circular motion. So now we say that we're summing the forces centripetally, and that equals m times a sub c, right? Because if you think about it, sure, these forces are sort of pointing in the y direction, depending on how we define our direction, but more importantly, they're pointing towards the center of the circle, and the block is traveling in a circle. So that's critical. And if we remember that Fc equals F net inwards minus F net outwards, F net out. So now we can solve for Fc, and we see that Fc equals, well, both of the forces are pointing inward, so we'll just say that this is equal to Ft plus Fg, and we don't have to subtract anything because nothing is pointing outwards. Okay, and we know that MAC is equal to mv squared over r by formula. So let's just put it together. We started with F sub c equals MAC, and now we have that Fg plus Ft equals m times v squared over r. That's our equation. And we're asked to find the force of tension. So let's solve for tension. We get F sub t equals mv squared over r minus Fg. What's Fg? This is one of the first forces we learned. Fg is simply m times g. It's the weight, so I'm just going to replace that right now with mg. And, well, let's take a look at what we're given. We're given that the block is 0.5 kilograms, so that's the mass. Let me just write that here. We're given the radius, a 1 meter string, right? Because it's traveling in a circle, and the string makes one endpoint, which is at the center, and the other endpoint is the block. So the radius is 1. That's radius. And we're given a velocity here, v. So we can solve for Ft, and we can get that this is equal to 0.5 times 10 squared all over 1 minus 0.5 times 9.8. And if we compute this out, we get this is 45.1 newtons. So that's at the top. I'll just put that there. So now what happens when we're at the bottom? Well, let's do a similar thing. Let's draw our free body diagram. So now the curve is pointed in the other, well, it's flip-flopped from before because now we're analyzing this part of the circle, the very bottom here. So at the bottom of the circle, the dot is there, and, well, what are our forces? As before, we have Fg, and that's still pointing down as it almost always should be. And again, we still have tension. Let me just draw what's going on here. So now we can imagine that's the string, and the block is at the bottom there. So if we're looking at the red diagram now, tension is pointing upwards, right? The string is upwards. And let's just do a very similar thing. The sum of the forces centripetally equals MAC, which is equal to M times V squared over R. So now what's FC? FC equals F in minus F out. And now we have something, well, now our forces are pointing in opposite directions, so we do have to figure out what is inwards and what's outwards. Inwards means towards the inside of the circle, so that would be Ft. And then out is outwards of the circle, so we subtract Fg. So now we're saying Ft minus Fg equals mv squared over r. We're solving for Ft, so we can add Fg to both sides, and Fg is equal to mg, so I'm going to substitute mg instead of writing Fg. And again, we have all of these quantities, we can just plug it in. This is 0.5 times 10 squared all over 1 plus 0.5 times 9.8, and this should give us 54.9 newtons, I believe. Let me just double check. I realized my picture was in the way. Yes, 54.9 newtons. Right? So we can see that at the top of the path and at the bottom, there is a substantial difference in the force of tension. So what does this tell us? It tells us that the force of tension is not constant, which is good, I think. I mean, we can't really talk too much about that. In this case, the difference between the forces 45.1 and 54.9, if we take that difference, we actually get 9.8, which is the gravitational constant, and that is mainly due to the difference between the computations here and here is that we have the same first term, but in the first calculation we subtracted this 0.5 times 9.8, and in the second one we added it. And that is due to our tension forces pointing in opposite directions. Our force of gravity pointing in opposite directions in terms of the circle. So they are pointing in the same direction downwards, but at the top, Fg is pointing inwards to the circle, and at the bottom, it's pointing outwards of the circle, and this 0.5 just made it be that the difference is 9.8. But the key thing to notice here is that at different points of the circle, the forces are pointing in different directions. It's not the case that just because a force points inwards to the circle, it will always point inwards to the circle. But that's not necessarily always true. So we see here that Ft, that points inwards to the circle at all times because the block is attached to the string. But Fg doesn't always point inwards to the circle. So that's the point I'm trying to make. We have to be careful of our forces and where we're analyzing our forces. With that said, let's move on to the next question. I'm going to quickly hydrate. I've been talking a lot, so let's just read this question in the meantime. Okay, hopefully you've had the time to read it. So now we're dealing with a horizontal circle. So from my demonstration previously, a horizontal circle is we're stirring the pot of food. So we're given some information about the string, the mass of the block. Let me just note that that's m. string, and we're given an angle. So previously we said that, oh, we're given the string is 1 meter, so that's the radius. But that's actually not the case. Let's just go back to this example here. We had a 1 meter string, and the reason for that is because this string created the radius. It's kind of tough to explain what's going on here, but if you imagine the string is tied down at the center, the other end is tied down at this block, the string creates the radius and the block just travels along that circle traced out by that radius. But what's going on here is that the string isn't the radius. If the string were the radius, the block would maybe go something like that, perhaps, or something different. The actual radius is this, from the center of the circle to the block that's tracing out that path. We're given that this is 1, and then we can sort of draw a perpendicular, and we can see that the point of contact with the ceiling is right above the center of the circle, and that's just by nature. That's how it works. It would not make sense for us to have this horizontal circle, this is the center, and then we have like some sort of ceiling here, and the block is tied here, right? This would not be a circle, right? Or rather, it would trace out the circle, but there's no way this block can travel the path I drew, because the string would somehow have to stretch to be that long at the furthest point, and that's just not possible. That's just not possible. And I mean, we can explain this a little bit further, but for now, you should be able to see why that this point where it's tied to the ceiling should be right above the center of the circle. And with a little bit of geometry, you can prove to yourself that that's true, but what I showed is just a quick sketch of what's going on and why that's the case. So with that said, we can find the radius, right? This is our radius, that blue R, that is the radius. Now I'll just make the line blue. And we can solve that using using trigonometry. So let's just draw it. We have this right angle, we want R, we're given that the string's length is 1, and we're also given this angle here is 60 degrees. So that tells us that this angle in red is 60 degrees. And well, that helps us out quite a bit, because we can take the cosine of 60 degrees, and that tells us that, well, the cosine of that angle is adjacent over hypotenuse, so that would be r over 1. So r is simply cosine of 60 degrees. Okay? So hopefully that's making sense thus far. Okay. So let's just see what's going on here. Let's just leave it as that. Okay, so we have R. We're asked to find tension. So tension is a force, obviously. So it makes sense to draw a free body diagram. So that's what we'll do. So let me just re-sketch what's going on here. We have this circle or something, and we're just at some point here, and there's like a string. So what are the forces present? Gravity should be one of the first things you're saying, and that's pointing downwards. There's also tension, because the block is tied to a string, and that tension force is along the string. So it's angled like that. There's no normal force because it's not on a surface, and there's no frictional force. Right? So that's sort of the free body diagram. And as we're so used to at this point, when we have these forces at angles, we kind of want to partition them into their components. So really, I want to have an Fty. I want to have this Ftx such that the vector sum of them equals Ft. and I want to have Fg still, because that's pointing downwards. So let's clarify what we mean by Fty and Ftx. Let me choose a different color. So this is Fty, or it's pretty close to it, and this is Ftx. But rather, before I draw Ftx, let's draw Ft. So Ft was something like this, and Ftx is like that, right? So we can see that if we take the vector sum of Ftx and Fty, so let's just do Ftx plus Fty using the head to tail method, we get that that equals Ft. So what I'll just do is I'm going to move Ftx upwards, so that way we form a little triangle here, Ftx. This is a right angle, and then we should be able to say something about the angles. We're given 60 degrees at the top here. So, well, where is that angle in relation to the triangle we drew? Ft is along the string, so those sides correlate. Ftx is the horizontal, so Ftx is the horizontal, which is with the ceiling. So it makes sense for this angle to be 60 degrees. Okay, so let's get Ftx and Fty in terms of Ft, because those are the Ftx and Fty is what we'll use since they're now in the correct directions. So let's just see, if we take the sine of 60 degrees, that's opposite over hypotenuse, that's Fty over Ft. This tells us that Fty equals Ft sine of 60 degrees. Similarly, if we take the cosine of 60 degrees, adjacent Ftx by Ft, that tells us Ftx equals Ft times this cosine, this time. Cosine of 60 degrees. Cool. So now we have Ft into its components. Our free body diagram is looking nice. We can sort of start to solve for Ft. So how are we going to do that? Well, we can sum the forces in certain directions. Okay, let's see. In this case, let's sum the forces in the y direction, because why not? Let's use a different color. Light blue, I suppose. So let's just sum the forces in the y direction. And that should be equal to m times a sub y. And it's important that we have the correct subscript here. It is indeed the y direction, for a couple of reasons. First of all, it's not the x direction, obviously, because x and y are just distinct. And then we also have to be wary that it shouldn't be f sub c. So in what instance do we have f sub c? That's when we are analyzing the forces that are causing circular motion. And certainly we do have circular motion here, but the forces involved in circular motion are those pointing inwards to the circle or outwards from the circle. Here, Fty and Fg are not pointed inwards or outwards to that circle. They're just pointed in the y direction. So we do have the correct subscripts. What can we say about the system in the y direction? Well, it shouldn't be accelerating. The block is traveling in a horizontal circle, which means that its elevation, or distance from the ceiling, isn't changing. It's staying at that same y level, which means it has no y velocity. If it was traveling in a vertical circle, then the situation might be a little bit different, because then the velocity is changing in the y direction. But since right now we're just stirring the pot, the y velocity isn't changing, so there's no acceleration in the y direction. Hopefully that makes sense. So we can just say that the sum of the forces in the y direction equals 0. So what are the forces in the y direction? In the positive y direction we have Fty, and the negative in the negative y direction we have Fg. That equals 0. We can say that Fty equals Fg do a little bit of substitution here. We just figured out that FTY equals FT sine of 60 degrees. We know FG is mg, so this tells us that FT is equal to mg all over sine of 60 degrees. And mass we're given is 0.5. I think may have messed up something in my answer key. That's all right. 0.5 times 9.8. All of this over sine of 60 degrees. And I don't have this, unfortunately, but let me just compute this really quickly. 0.5 times 9.8 divided by sine of 60 degrees. What do we get? This should be equal to 5.66. And our units are newtons. Does that check out? Yeah, it should. So that is the tension in the block. And that was the first part of the question. We also have to find speed, but we can see that, well, we already calculated tension and we didn't have to worry about circular motion. So this was just a nice review question of what we've done previously. But now we have to find the speed, and that's a little bit more complex, because now we actually have to consider circular motion, because the speed comes from the block traveling in the circle. So now let's sum the forces in the circular direction, if you will. So F sub c equals MAC. We only have one force pointing in the circular direction, and that is FTX right there. So we say that FTX equals m, and then a sub c equals v squared over r. We need to make that substitution because we're solving for velocity. Let's just rearrange so we can solve for velocity. This gives us that r times ftx over m equals v squared. And then v is the square root of that quantity, but we know that ftx is equal to ft times cosine of 60 degrees, all of this over m, right? That's that. And well, we have all of these quantities. ft, we just solved for it, that's 5.66. m, 0.5, we were given that. r, we solved for to be cosine of 60 degrees, so we just plug in everything. V equals the square root of, not 0.5. R is cosine of 60 degrees times 5.66 times cosine of 60 degrees. All of this over 0.5. And the square root of that, again, I don't have that calculated. So let's try to calculate this. 5.66 times that times cosine of 60 degrees times cosine of 60 degrees. And this gives us 1.68 meters per second. Awesome. Okay, so now we've familiarized ourselves with horizontal circles and vertical circles. So things are starting to be put together, and you'll notice now that even though I labeled the force vector ftx, when I summed the forces, I did not sum the forces in the x direction. Sure, it was pointing in that direction, but more importantly, it was pointing in the circular direction. I really shouldn't be saying the circular direction, but it was pointing inwards towards the center of the circle being traced out. So that's that. Wow, we are powering through this. Okay, so now we have some beautiful diagrams. So first, let's read the question. We have a car traveling velocity v around a banked curved surface of radius r. So there's that word that we learned at the beginning. And now it's saying, at what angle should the road be banked such that the car can negotiate the curve without the aid of friction? So that's just saying that the car should be able to safely travel along this banked surface and not have to worry about like flying off because of friction or whatever. So we have the side view on the right. So the little box with two circles underneath it is a car, and it's going in like this direction. So we can sort of imagine that like the surface is like a circle type thing here. I can't draw very well, but it's like, and it's like banked throughout. So it's still something like that. But it's a circle and it's traveling along the circle. I just made that drawing much worse than it needed to be. But hopefully that makes sense about what's going on there. I'm going to erase some of this to give me some room to solve the question. So first let's draw a free body diagram, because why not? What are the forces going on here? Well, hopefully you're screaming out gravity, gravity, and you should be, because gravity is present. So gravity points downwards. And let's see, normal force. Well, the normal force is perpendicular to the surface. So since the surface is at an angle, the normal force should also be at an angle. So in this case, the normal force looks something like that. There's no friction because without the aid of friction, there's no tension because there's no strings or anything like that. So that's the free body diagram. And really, well, we're curious about the angle that they should be banked at. So we want this angle theta. Where can we find theta in our free body diagram? Well, you should be able to convince yourself that this angle here, this angle here is theta. I don't want to spend too much time getting into it, but really you have two options. Either it's the one I drew or the one that's complementary to it right here. And with a little bit of geometry, you should be able to figure out why the angle that I gave as theta is actually the correct one. And since we have Fn at an angle, we really kind of want our free body diagram to, have components. So we want to have Fg pointing downwards. We want to have Fn in the y direction and Fn in the x direction. So to do that, we can use a little bit of trig. So I'm just going to go off to the side here, draw a little triangle because we've seen this before. This is theta. This is Fn. This is Fnx. This is Fny. So what I'm doing right now is very similar to what we did up here with tension. Now we're just doing it with the normal force. And if we take the cosine of theta, we get that is Fny over Fn, which tells us that Fny equals Fn cosine of theta. And similarly, if we take the sine of theta, that is Fnx over Fn. So that tells us Fnx equals Fn sine of theta. All right, so now we have a free body diagram broken into the x and y components, looking good to go. We've solved for some of those components. We're in good shape. So now it seems time to sum some forces. So let's do that. Let's take a look at the y direction first, because the car isn't accelerating in the y direction. It's staying at that same that same height, same position in the y direction. So the acceleration in the y direction is 0. Well, what are the forces pointing in the y direction? We have Fny pointing upwards, and we have Fg pointing downwards, and that's equal to 0. So we can get that Fny equals Fg, and more importantly, just do a little bit of substitution. We solve for Fny. We said that was Fn times cosine of theta. That equals mg. And okay, well we can sort of solve for theta here, right? But we still need to figure out what Fn is. We have m. Well, we don't really have m, but we have g. So it seems like we didn't really get that far. But that's okay. We still have another direction to sum the forces in. So now we'll sum the forces centripetally, because we're traveling in a circle. And which force is providing that circular motion? Well, that's Fnx. We can imagine that the path that the car is tracing out to be a horizontal circle. That's a pretty bad drawing. But like, it's going around this track in a horizontal circle, and which force is pointing in that direction? That is Fnx. So we have Fc, that equals MAC, MAC. So Fnx equals MAC, but we know that AC is equal to mv squared over r, so rather AC is equal to v squared over r, so MAC is mv squared over r. There's a lot of variables to worry about. And, well, Fnx is equal to Fn sine of theta, and we said that equals mv squared over r. And, well, we can sort of do some sort of substitution. We have Fn here, we have Fn here. So let's just solve for Fn at the top here, right? This is Fn equals mg divided by cosine theta. I'm just doing this because I want to make the substitution in for Fn, get rid of this Fn term, because we don't know what Fn is equal to. To calculate that, we would need the angle theta, but that's what we're solving for. So let's just make that substitution in and see what happens. So this tells us mg divided by cosine of theta times sine of theta equals mv squared over r. And what we can see is that the m's cancel, which is a very good sign because we didn't have mass to begin with, and I was starting to worry. So let's just simplify this a little bit. This tells us that g times sine theta over cosine theta, so let's just say that that is tangent of theta, equals v squared over r. And we're solving for theta, so let's just isolate that. Tangent of theta equals v squared over r times g. So theta equals the inverse tangent, v squared over r times g, and that is our answer. Awesome. This is a very important question. Banked curves are a very popular topic for circular motion, for obvious reason, because they're present in the real world. Instead of analyzing me stirring a pot of food, we're now analyzing NASCAR cars, although not quite because their track is elliptical, but this is a nice approximation. So this is a little bit more exciting. So yeah, banked curves, very important. In this problem, we neglected friction. We didn't neglect it, we just solved the problem such that we wouldn't need friction. But there are instances in which there is friction present. And yeah, that just introduces a new force, and it's solved relatively similarly. Okay, let's move onwards. We have just a couple more questions, so we're probably going to end early, which is a-okay. This is a fun question. So, riders in a carnival ride stand with their backs against the wall of a circular room of diameter 8 meters. The room is spinning horizontally about an axis through its center at a rate of 45 revolutions per minute when the floor drops so that it no longer provides any support for the riders. And we're asked to find the coefficient of friction between the wall and the riders such that the rider doesn't slide down. Okay, so you might be like, what in the world is going on? And that's a fine question to ask. So, with my wonderful artistic skills, I'll sort of draw what's going on. So what they mean by circular room is basically a cylinder. And there's some axis here, and it's spinning around this axis. So I'll just draw a little arrow like that, showing that it's spinning. And what happens is we have a person, and originally there's this like surface here which they're standing on. I can't draw it too well. But as the room is spinning, the floor goes away. So now it's just the person there, and they're stuck against the wall due to the centripetal motion. And also due to the friction between them and the surface. And so you're just spinning without any surface below you. So that is what is going on. I do not like roller coasters whatsoever. So even though this isn't really a roller coaster, it's kind of a ride. And I thought it was pretty tame when I tried it out. This was when I was a child. I was still terrified. It is not fun to be spinning around at a very high rate, and all of a sudden the ground below you disappears, or it drops below you, and you are stuck against a wall, and you have nothing to do except to trust physics and that you don't fall off. Absolutely terrifying. Okay. Maybe I'm exaggerating a little bit, making it quite hyperbolic. It was not fun. That's the point I'm trying to make. Though I highly encourage you to ride it if you get the chance, because it's a good lesson for physics. Anyways, back to this. What's going on here? We're given the diameter of the room is 8 meters. So if we just take a look at this, let's just have the radius be 4 meters. And we'll draw 2 of those, because really we care a lot about the radius with these problems. So that's, I'll just write it up here, r equals 4 meters. We're given the velocity, sort of. It's in revolutions per minute, so we're going to have to do some dimensional analysis with that. And we're trying to find mu. Mu is what? So, as always, we should do a free body diagram. So, in this case, the name free body is quite appropriate, because we are looking at a body, and the body is quite free in that there's nothing really supporting it. But actually, there is quite a lot supporting it. So let's just let this dot be the person. What are the forces present? As always, we should be saying gravity, and we would be correct in saying that there is gravity. And then we should be saying that there's frictional force, because we're tasked to find the coefficient of friction. So there's friction, there's no tension because there's no strings. There's also a normal force. And this is really strange. The normal force is when the object is on a surface, and it clearly is on a surface. The person is relying on the wall behind them. The wall behind them is the surface. So there is a normal force, but where is that normal force pointing? Perpendicular to the surface. So get ready for this. Our normal force points like this. Mind blown. We're so used to saying, okay, that's our object, here's Fg, this is Fn, right? Something like that. And then sometimes if we're feeling particularly excited, our normal force is something like that, you know. We're accustomed to that. Now, everything's out the window. Now the normal force is perpendicular to gravity. So not only is this ride completely bonkers, but the physics behind it is also quite bonkers. And we haven't even gotten into it much. Now we have to figure out friction. And this is also quite weird. We should remember the definition of friction is that friction points in the direction opposing motion. So we don't want the rider to slide down the wall. We need friction to keep them from sliding down the wall. And if they were to slide down the wall, that would be due to the force of gravity. So the force of friction should oppose that direction, and friction points upwards. What is going on? That is the weirdest free body diagram of all time. Unbelievable. Okay. This is exciting. We have a very strange free body diagram. So, we want the rider to be balanced, right? When the floor drops, we want them to be balanced. They should be clinging onto the wall for dear life. But what am I trying to get at? I'm trying to say that they should not be accelerating in the y direction. If they were, they're probably falling down, or the friction is too strong that it's pulling them upwards, but we don't want that to happen. We want them to stay where they are. So there should be no acceleration in the y direction. So if we sum the forces in the y direction, that should be equal to 0. So let's sum the forces. FF minus FG equals 0. What a strange equation. We've never seen something like this. This tells us that FF equals FG, and this tells us mu times F sub n equals mg. So we want mu, and we don't have m, but we have g, and we don't have F sub n. But we can figure out F sub n, because that's a force present in our free body diagram. So to do that, we would have to sum the forces, and in this case, we're going to sum the forces centripetally, because Fn is pointing towards the center of the circle, the circular path that the person is traveling, right? So this person is traveling this circular path along the room as this entire cylinder is spinning, right? It traces out that path, and this is Fn. So Fn is the centripetal force, and this equals MAC, which is mv squared over r. Okay? So, well, just by substitution, we say that Fn equals mv squared over r. We don't have m, that's okay. We have r. We sort of have v. We're given v is equal to 45 revolutions per 1 minute. And previously in another question, we were given revolutions per second, and we needed to convert it to meters per second. Very similar thing here. So we'll do a little bit of dimensional analysis. First, let's take care of the revolutions. So 1 revolution, we remember, is the circumference. So 2 pi r, which is 4 meters. So now we have it in meters per minute. So now we have to take care, in 1 minute, there's 60 seconds. And if we do this multiplication out, we get this is equal to 6 pi meters per second. So now our velocity is in good shape. Okay, let's just take a look at this equation up here, and let's just solve it for mu, because that's what we're curious about. Mg over Fn. And now we can make a substitution. Mg over Fn. We have Fn is equal to this, so we can substitute that in, and we get mg over the quantity, mv squared over r. So that's saying this is equal to mgr over mv squared. Thankfully, the masses cancel. Once again, I was worried about the masses, but they happen to cancel. So maybe when you're solving questions and masses cancel, maybe you should feel confident about yourself that, I've seen this happen before, so it's not a mistake. So mu is equal to gr over v squared. We have all of these quantities, 9.8 times 4 all over 6 pi squared. This gives us 0.11. The coefficient of friction does not have units. Our answer is B. Awesome. This is one of my favorite questions. It ties together so many different things. We did circular motion in this question. We revisited friction, calculating the coefficient of friction. We saw the most random free body diagram of all time, and we got to analyze a pretty cool carnival ride, which I'm still scared of. But yeah, that's that. Okay, with that said, we're going to move on to the last question of the day. And unfortunately, it has multiple parts. I'm sorry, but that's just how it rolls. But it's not too bad. So we have a coin that's on a disc at some distance, and the disc rotates counterclockwise at a constant rate. That seems important, perhaps. And the coin does not slip. And it takes 1.5 seconds to make a complete revolution. So let's revisit this. It does not slip. What does that mean? That means that as the disc is turning, the coin isn't going like randomly elsewhere. It's in place, in a sense. So if I were to draw out the path that this coin takes, Oops, that is not right. It travels in a circular path at the same distance from the center. Let me just draw a better circle. Something like this. Like, you can imagine what I'm trying to say. So it's traveling on that circular path at the same distance from the center. So it's not slipping. Okay, so here we're asked to draw and label vectors showing the instantaneous acceleration and linear velocity vectors for a coin and its position. Okay. Well, that shouldn't be too hard. It's spinning anti-clockwise. The velocity vector should be tangential. So let me just redraw this circle here. And so the tangent line at this point looks something like that. So the velocity is either pointing this way or this way. And it should be kind of clear that it should be pointing upwards because the disk is turning anti-clockwise, so we want the velocity vector to be pointing in the same direction that it's moving, right? The same direction that the disk is turning. So that is our velocity vector. And acceleration is the other thing we want to label, and that we should remember is pointing inwards. So that's our acceleration vector. So that's part A, pretty simple. Now we have parts B, C, and D. So now we want to find the linear speed of the coin. So this is saying velocity equals what? We can figure this out. We're sort of given velocity. Again, we see the word revolution. And what is this saying about revolution? In 1.5 seconds, the coin makes a complete revolution. So 1.5, I don't want to do it like that. 1 revolution in 1.5 seconds, that is sort of the velocity. We can just figure out what it is in terms of meters. How much is 1 revolution? Well, that is just 2 pi r. But what is r in this case? Well, it is the distance from the center to the edge of the circle. And in this case, the edge of the circle is the circle traced out by the coin. So I guess I have to draw it on this diagram. So now it's angled. So it's the 0.14 given to us. That is the radius. It's not this distance because the coin isn't at the edge. It's closer to the center. So this is equal to 1 over 1.5 times 2 times pi times 0.14 over 1. And when we do this computation, this should be 0.6 meters per second. So that's part B. I'm going to add a page. Okay. So now, let's look at part C. So now the disk has an increased rate of rotation. And we're given the coefficient of static friction. And now we want to find the velocity of the coin when it just begins to slip. So now the circular path isn't being followed as much. So the coin will begin to slip when the static friction has reached its maximum. That seems a little bit confusing. Let's just dive into what we need to do, and we'll explain it. So when we're confused, we should probably draw a free body diagram. So this is the coin, and this horizontal line is the surface that it's on. So we're looking at it at eye level. We're not looking down on it, we're looking at the same level as it. Oh gosh, my voice is starting to go. What are the forces present? Gravity. No comment. Normal force. It is on a surface, there should be a normal force. Fn points this way. And now we have the frictional force. The frictional force points inwards. It opposes the motion. So now let's sum the forces in certain directions. Let's do the y direction. So not accelerating in this direction. So the sum of the forces should be 0. This tells us Fn minus Fg equals 0. And more importantly, Fn equals Fg, which is mg. Now let's sum the forces centripetally, because the coin is traveling in a circle, and Ff is providing that centripetal force. This is equal to MAC. We get Ff equals mv squared over r, just simple substitutions that we're used to. So now we see that, okay, mu times F sub n equals mv squared over r. And well, we have Fn, that is mg, so mu times mg equals mv squared over r. So we divide both sides by mg, we get mv squared over r times mg. Masses cancel. This is v squared over r times g. So that's that. What are we trying to solve for? We're trying to solve for the linear speed, which is velocity. So we get v squared equals mu rg, v equals square root mu rg, and we are given all of those quantities, so we can just plug it in. 0.5, radius is still 0.14, 9.8. It's still 0.14 because it's right before the coin starts to slip and we can't track its path. So it's still traveling in a circle at that last moment. If we compute this out, we get 0.83 meters per second. And that's part C. And now we have part D. And this is saying we do the same thing in part C, but now another coin is glued on top of the first coin. So now here we have, let me just erase this. We have another coin on top. So what happens to our answer in part C? Well, let's think about it. When a coin is glued on top of another coin, I can just treat that as one total coin with the same mass as the combined coins. So like if the first coin had mass m and then we glue another coin of mass m on top of it because it's identical, I can just treat that as one coin of mass 2m. So if we look at our equation for v, which is what we're asked to look at, that only depends on mu, r, and g. So for d, the velocity does not change. Does not change. Because velocity depends only on mu, r, and g. And even if we look here, in our calculations to eventually solve for v squared, we canceled out the m's. The mass is canceled. So the velocity does not change, even though we have a larger coin. And that is the last question. There is one more question, but we're not going to touch that today just because I don't think it's a worthwhile problem to do. So that'll end today's lecture on uniform circular motion. This is a really, really important unit. So hopefully we learned a lot. If there's one thing that sticks with you, hopefully it's the difference between a horizontal circle and a vertical circle. But obviously I hope a lot of other things stick with you. But yeah, that is going to end today's content on uniform circular motion. Feel free to re-watch some parts of the video. Some questions I may have sped through a little bit quickly, or just to gain some insight onto how we approach problems. But yeah, that will conclude today's lesson. As always, thank you for watching. On Wednesday, we will be doing calculus, and Thursday, we will be doing physics C, back to our normal scheduling. So yeah, until then, I will see you on Wednesday. So take care.